And out for everybody. Focus here. Paper, where's the paper? So, I guess before we get started, any comments, questions, concerns, thoughts about your exam yesterday? It's fine if there are none, but if you wanted to ask, I have no idea what was on it, but if you remembered something that you had a question about, you could happily go over it, or we could just forget it and move on, because what we're moving on to is a total shift from what we've been doing. Well, if anything comes up about it, you're always welcome to ask. But we are moving on to counting things, essentially. Really, I mean, really what we're talking about or we're leading up to is probability and trying to calculate the probability of something happening, essentially. There's something else to say here. Right, we have 2 weeks left, right? We have today, Friday, Monday, Tuesday, Wednesday of next week, and then Monday through Friday of the week after Thanksgiving. That's it. So you've got 6 more class meetings. What, Friday, Monday, Wednesday? Are you guys meeting on Wednesday? I mean, you don't obviously you don't have to ever go to class if you don't want to, right? But like if you're you should at least be be aware of what's happening in class on Wednesday and then the week before finals. So not a lot of days left to cram in this probability stuff. So let's get to work. And really, what I would point out is when we're talking about probability, it's mostly about carefully counting what's going on. So we're going to eventually try to find the probability of some event happening. And usually we're going to calculate that is by calculating the number of ways that specific thing can happen divided by the total number of ways kind of anything can happen. That's the really kind of large perspective is what's going on here. But we have to build that up. So we're going to first talk about the principles of counting. You're like, what? It's just counting. Well, yeah, but there's some ideas behind how to count things when there's more to count than just what your fingers can handle. So, oh, and let me turn off the light here. Yeah, much better. Okay. So really, this is best done through some examples. So here's one example that's not particularly realistic, but it works for the intended purpose here. Planning your schedule for next quarter, and you're going to take a stats course, a bio course, a chemistry course, and a music course. And just for the sake, I know this is not very realistic as far as UC Davis goes, but for the sake of making our schedule, there are 4 stats classes to choose from. I should say 4 sections is what I actually meant. 4 stats sections. So you're taking stats 13, and there's 4 different sections to choose from. And similarly, there are 2 sections of whatever bio class you're taking. There are 3 sections of whatever chemistry class you plan on taking. And there are 2 sections of the intro to music class. I think that's music 10, maybe. And the question we're going to answer is how many different schedules can you make? Assuming, right, there's no like overlap between classes, like all the normal things you would actually have to consider, we're ignoring those. So how many different schedules could you make? Or in other words, how many different combinations of one stats class, one chemistry class, one bio class, and one music class are there? Well, it's all about the number of choices we have. So let's say we picked the first section of stats. Well, if we pick that first section of stats, then we can either pick the first section of bio or the second section of bio. And based on that choice, we can either pick the first section, the second section, or the third section of chemistry if we pick the first section of bio, or if we pick the second section of bio, any one of the three chemistry sections. And then the picture is about to get really kind of too big here, but for each chemistry section, there are two choices of music sections, the first section and the second, and so on and so on, right? So each of these would have two. So, and then we could repeat this diagram for each different section of statistics. So for the second statistics section, we'd have the same number of branches going all the way down to, and then so on and so forth. I don't really want to draw all of it. So, and then, right, for S3, the same stuff. For the fourth section of stats, the same stuff. So if we counted all these up, if we counted all the different pathways, let's see, there's 1, 2, 3. Basically, every different M at the bottom of this picture, which I didn't fully draw, is a different combination of a stats, chemistry, bio, and music class. If I count this all up, well, let's see. At the bottom here, there would be 6 plus another 6 would be 12, and there'd be 12 for each one of these. So I think there'd be 48 in total. It seems like a lot of work to do to figure out how many there are. Well, it is. There's a much easier way. We're just going to multiply the number of choices we have together. So there's 4 different stats classes we can choose, times 2 different bio sections we can choose, times 3 different chemistry sections we can choose, times 2 different music sections we can choose. And if we multiply those numbers together, we get 4 times 2 times 3 times 2, which is indeed 48 different possible schedules. And that's really the idea of the multiplication principle, is that if you've got some number of choices that don't really kind of depend on each other, you can just say, okay, how many choices do I have for this first thing, times how many choices do I have for the second thing, and so on and so on and so on until you've exhausted everything. It seems pretty straightforward, but occasionally it can be a little confusing depending on what's happening. So it's always good to kind of make sure we're reading carefully about what's happening. Let's look at another example. Oh, and also there's a handout over there that you should grab when you have a chance. It's basically just some probability terminology, as well as on the backside how playing poker works. Because we will talk about some poker examples eventually, which you need to know how poker works if you want to talk about poker examples. So let's look at another example of the multiplication principle. And this one's a little bit more words. In a study of the effects of light and fertilizer levels on plant growth, we plan to study or test 5 different fertilizers and 3 different light levels. We also don't just want one plant for each possible combination of fertilizer and light, because maybe that plant is, deficient in some way or extra great. So we want 4 replicates or 4 plants for each fertilizer and light combination. So how many plants do we need to go by? It's a lot of writing for a pretty straightforward answer. There's 5 types of fertilizer times 3 types of light times 4 plants for each one, which is going to be 60. You can also draw a picture if it helps, right? You can think of like, okay, you have fertilizer 1, fertilizer 2, fertilizer 3, fertilizer 4, fertilizer 5, and that's going to be under light level 1, and under light level 2, same deal. Under light level 3, same deal. So there's obviously 15 different combinations of a fertilizer type and a light level, and then each combination needs 4 plants, and 15 times 4 is going to give us 60 plants. So again, we're just multiplying stuff together. I know it seems kind of straightforward, but don't worry, it'll get more complicated. Or worry, it'll get more complicated. So let's look at this next example. The genome for HIV contains 9,749 nucleotides. I will just briefly mention here, some of these questions do involve some basic knowledge about biology, typically like how there's like 4 different types of the A, C, T, and G, what are they like? Proteins? I have no idea. I don't know jack about biology. What's that? Yeah, the DNA things, right? The A, C, T, and G. What are those things called? Who knows? Lots of you probably. I don't. But okay, you should know stuff about biology and like genotype, phenotype expression, which is kind of explained on that little handout. Um, so maybe they're called nucleotides. I don't know. There are 4 different types of nucleotides. How many genomes are possible? So what we're really asking here is there's 9,749 different slots for a nucleotide. So there's 9,749, no, that's a big number, 9,749 nucleotides. And in each slot, you have 4 different possible nucleotides that could go in there. So in your first slot, you have 4 choices. In your second slot, you also have 4 choices. In fact, in every slot, you're going to have 4 choices, whether it's the first, the second, the third, or all the way down to the 9,749th. And if you multiply those 4s together, I don't know what that number is, but I know how to express it. It's 4 to the 9,749th power. And that's the best way to write our answer here. That number is probably too big for our calculator. Like he's probably going to get an error, an overflow error, depending on the calculator. Okay, so multiplication principle, not that exciting, but definitely useful. Moving on, let's talk about permutations. And I would say broadly, when you think about a permutation, we think about the fact that the order of arranging things matters. So it's usually, we're talking about the number of arrangements or the number of ways of ordering some fixed set of things. Number of arrangements where we usually think about the order matters. So when I say order matters, it means like if you have A, B, and C versus A, C, and B, those are different things because they're in a different order. So let's look at this example. 4A. So at the library, they do have books, in case you didn't know. And we're looking at a shelf that happens to have 4 different math books on it, 5 different chemistry books. I mean, I don't know what shelf in the library this is because the math books and the chemistry books usually aren't right next to each other, but okay. And 6 different biology books. Maybe it's like the return shelf and they're just organizing stuff. The first question is going to be, how many different ways can we arrange the books on the shelf? So in this case, order matters, right? Since all the books are different and I'm asking how many different ways there are to arrange them, which book I put furthest left makes a difference. So when I start thinking about my 15, let's see, 4 plus 5, yeah, 4 plus 5 plus 6 is 15. I start thinking about my 15 different places to put my 15 different books. 7, 8, 9, 10, 11, 12, 13, 14, 15. So Here's the way we usually think about a problem like this. We pick a side to start on, usually the left, although it doesn't really matter. And you ask yourself, okay, for this first slot, I haven't put any books on the shelf yet. How many choices do I have for that first slot? Well, there's 15 books to choose from, and I haven't used any of them yet. So there are 15 possible choices here. And now we're going to imagine that we have chosen one of the books and put it in that spot. And then in the next spot, from the remaining 14 books, there are 14 choices. And that process kind of just continues the whole way down. In the next slot, there are 13 choices, and then 12, and then 11, and then 10, and then 9, and then 8, all the way down to 1. That's a pain to write. There's a much more compact way of writing that. This is equal to 15 factorial, which is what the exclamation point means. So when you see a number with an exclamation point, that just means that number, and it has to be a positive integer. It can't be a fraction. It can't be a negative number. I should rephrase slightly. It has to be a non-negative integer, meaning it could be 0. We'll talk about that in a minute. It's not that important. It just means multiply that number by all the numbers smaller than it all the way down to 1. Unless you're talking about 0, which we'll talk about in a minute. So that's how many choices there are. And it's kind of a big number. It is worth knowing that on most calculators, and certainly in Desmos, if you use the exclamation point, it'll calculate that for you. Is it on my calculator here? Probably. So looking at this calculator, can you see that all right? Yeah, kind of. Yeah, you can kind of see that, right? I guess I can look here instead of trying to look at it. Yeah, sure. So just to point out, if you wanted to calculate 15 factorial, you would probably go to the, I want to say the stat button here. Nope, that's not what I want. I want the probability button. And then you go down to the little exclamation point, and then you press enter, and it's a very large number. But that's how you could calculate something like that. A more interesting thing might be something like 5 factorial. 5 factorial is 120. 5 times 4 times 3 times 2 times 1. 120. So these things we're talking about, there are definitely, if you actually had to numerically evaluate them, there are places to do that on a calculator where you don't have to type in the 15 times 14 times 13 times, right? Like, don't do that. There should be an easier way to do it. So what if we ask the same question, except now we're going to have an additional requirement. How many ways can we arrange the books if all the books of the same subject have to be next to each other? Have to be adjacent. Okay, well, you kind of just have to make a choice to start off with. So let's say we're going to have math first, and then chemistry second, and then biology third. And let's see, there were 4 different math books. So there should be 4 factorial ways of arranging them, right? There's 4 times 3 times 2 times 1 ways of ordering the 4 math books. And that's just 4 factorial. For the chemistry books, there were 5 of them. So there's going to be 5 times 4 times 3 times 2 times 1, which is just 5 factorial. And for the biology books, there were 6 of them. So there's going to be 6 factorial ways of arranging them. But that's not the whole story. We didn't answer the question fully. There's no reason the math books have to be left most. We could have put the biology books left most or the chemistry books. So we also have to include the number of ways we could order the different subjects. How many subjects are there? 3. So there's 3 factorial ways of picking what order they go in. It could either be math, chem, bio, math, bio, chem, bio, math, bio, chem, math, bio, math, chem. That's 6, which is 3 times 2 times 1. Or just more easily, 3 factorial. Times 3 factorial for the number of ways we can permute, order, arrange, whatever words you want to use, permute the different subjects. And you should leave your answer like this. right? Unless someone really specifically says they want you to like give a number multiplied out. Like there's no good reason to not to everyone knows what we mean, right? There's no good reason to say it's whatever large number it happens to be. So, very broadly, the number of arrangements, also called permutations of n objects is n factorial, which is equal to n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Let's see. What do I want to say here? What else I want to say? So, no, we'll say that in a minute. We're not quite there yet. So, here is a not terrible question. How many distinct ways can we arrange the letters in the word math? Well, there's four different letters, so we have four factorial ways of arranging them. And even though I don't typically like to write things out because it's kind of a long list, right? 4 factorial is equal to 24. I'm going to write them out so we can see how it's different than the next answer. So you probably don't want to write this out, but you certainly can. But I will talk about kind of the way I organize my thoughts when I'm trying to write out the whole list of things, because occasionally you might have to write out a whole list of things. Hopefully not very often. But I'm going to start with the smallest number first, the letter closest to A first. So I probably start by writing this as AHMT. There's my first arrangement. Sometimes people call this a word, by the way. So in math, when we talk about rearranging letters, someone could say, what are all the words you can get by arranging the four letters in the word math? And when they say the word words, they don't mean actual words that you would like look up in a dictionary. They mean literally any dumb arrangement of these four letters, even if it doesn't actually make a word that you can find in the dictionary. So this is a word as far as mathematicians are concerned. Okay, so here's what I usually do. I start by working at the end. So I'm going to switch the M and the T. So I got A, then H, then T, and then M. And then I've gotten all the possibilities with A and H first. So then I'm going to make the H be not first. Or it's not second. I'm going to have A, then M, then H, then T. Or A, then M, then T, then H. I'm done with AH. I'm done with AM. I need AT. A, then T, then M, then H. A, then T, then H, then M. I've exhausted all the ways of putting A first. So now I repeat the process, putting a different letter first, like H. H, then A, then M, then T. H, then A, then T, then M. And then H, then something next. So M, A, T, H, M, T, A. And then H, I've done A, I've done M, I need T. H, T, A, M, H, T, M, A. Okay, it's a little bit exhausting, but it is worth the time. So then finally, we're not finally. Next, we'll do M, A, T, H, M, A, H, T, M, H, A, T, M, H, T, A, M, T, A, H, M, T, H, A. And finally, putting T first, T, A, M, H, T, A, H, M, T, A, sorry, not T, A, T, M, H, A, T, M, A, H, T, M, not T, M, T, H, A, M, T, H, M, A. There's all 24 different ways of arranging the four letters in the word math. And I should say they're all distinct because all the letters are different. So we don't really think about where you might be double counting something. So this question is different than part B here. How many different ways are there of arranging the letters in the word data? And now the answer is not going to be 4 factorial because even though we could think of this as like A1 and this is like A2, and we could write down all 24 of them, any place where you could switch A1 and A2 and get something else is still going to look the same. Here's what I mean. I don't really want to write them all out, but I'm going to. So we could have A1, A2, TD, or A1, A2, DT, or A1, DA2T, A1, DTA2. And then we have A1 TA2D, A1 TDA2. All right, so that's the first list starting with A1 first. Now the next list is going to start with A2 first, and you will observe that all of these we've already got. I already have AATD. I already have AADT. I already have, oops, sorry, maybe I should stop talking while I write these things down. A2D, A1D, A2D, TA1, A2T. I'm doing something interesting here, James. Oh, that's right. I'm not looking at the letters very carefully here. That's the problem. Cool. And then finally, A2, TD, A2. So each of these is, right, this is AATD, this is AATD, this is AADT, this is A, right? These are all the same. I don't want to count all 12 of these. I only want to count 6 of them because only 6 of them are distinct. And similarly, we could write down the other 12, which I don't think we really need to do, to say that they're going to also be doubled up. So the way we're going to calculate this is we're going to say it's 4 factorial divided by the number of ways you could interchange all the letters that are the same as each other. So there are 2 factorial ways you could interchange the two A's. 2 factorial is just 2. So this is going to be 24 divided by 2, which is 12. So there are 12 ways of arranging the letters in the word data to get something distinct. I've only written 6 of them down. There's two more columns here. But that idea holds. So for example, if I said, how many ways are there of arranging the letters in the word statistics? Well, first I would just look at the total number of letters. So say, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. So there's going to be 10 factorial ways of permuting those 10 letters. But there's going to be quite a few where I'm really just having the 3 different T's moved around. Like I could move T1, T2, and T3. I could permute those in 3 factorial equal to 6 different ways and still get the same result. I could have T1 here, T2 here, T3 there, or T1, T3, T2, or T2, T1, T3, or T2, T3, T1, or the other two, whatever they are. So I need to divide by the number of ways I can reorder the T's, the number of ways I can reorder the 3 S's, also 3 factorial, and the number of ways I can reorder the 2 I's. If you want to get real annoying about it, you could also say throw in a 1 factorial for the lone A and a 1 factorial for the lone C. But it's not necessary because 1 factorial is just 1. And multiplying or dividing by 1 doesn't change anything. Oh, there's someone online. Let me, one moment, sorry. Let me give you the attendance form. Speaking of the attendance form, let me give you all guys the attendance form too. Where'd my video go? Where did my video go? That's weird. Did I not turn my video on? Nope, I'm on. Strange. That's bizarre. Okay, well. All right, cool. So, attendance form. I'm thinking about it. Not set from that. Okay, still talking about permutations. I feel like I lost it over here. Sure. Six. Um, in a jam, in a jam contest, which you might observe at your local county fair, with 10 entries. Or sometimes they have like place setting. Have you guys ever been to the Yolo County Fair? You should go like next year, and it's like for a week or two. But they have like place setting competitions, and some of the things are really elaborate. Like it's not what I would have imagined. The people get really into place settings, which is okay. How many different ways can we award first, second, and third prize? So a couple ways to think about this. One way to say, well, how many possible choices are there for the first prize jam? Well, how many entries are there? 10, right? There's 10 different people we could pick to be first place. But then after we picked our first place jam, there's only 9 entries left to pick second place from. And then there's only 8 entries left to pick third place from. So there's 10 times 9 times 8, which is 720 possible ways of awarding first, second, and third prize. Here's another way to think about this. You could say, I want to imagine I'm going to think of all the ways I could order or rank all 10 jams, which would be 10 factorial. But then you know what? We don't really care about how the bottom 7 are ranked. So we're going to divide by all the ways you could reorder the bottom 7 places, 4th, 5th, 6th, 7th, 8th, 9th, and 10th, which is 7 factorial ways. You know what that's exactly equal to? It's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. And these parts exactly divide out to 1. So we get the same exact thing. 10 times 9 times 8, which is 720. If there's something else I wanted to mention here. No, I guess not. So there actually is a formula for the number of ways of permuting k things out of n things. And it looks like what we have here, 10 factorial divided by 10 minus 3 factorial equals the number of ways of permuting 3 objects from a list of 10 objects. I don't love this formula because there's not really good notation for it, but the more generalized version is the number of permutations of k objects chosen from a group of n objects is notation. You can write P of parentheses n comma k. There's also lowercase n, capital P, lowercase k. That's how it looks in your calculator. And it's equal to n factorial divided by n minus k factorial, which is what we just did. So here's actually an interesting place to talk about something that's not super duper important, but is a tiny bit important. So what if the question was, how many ways can we award first place through 10th place to our 10 jams? Well, this is kind of a longer way of describing, I just want to know the number of ways I can reorder the 10 things. So the obvious answer, I think, is just 10 factorial. But I want to point out that the formula makes us have to have something interesting happen. And that's not the right formula. The formula is going to show us something that has to be true. So using this formula, if I want to find P of 10 comma 10, which I know is supposed to be 10 factorial, I'm going to get 10 factorial on top and 10 minus 10 factorial on the bottom. But if I want this to equal 10 factorial, the bottom had better be equal to what? If I want this to equal 10 factorial divided by what number is going to still equal 10 factorial? It's got to be 1. There's no other choice. What this means is that 10 minus 10, which is 0 factorial, 0 factorial is defined to be equal to 1. It's kind of similar in nature to how something like 5 to the 0th has to be equal to 1, because there are arithmetic rules that we have all agreed upon, and this is one of the consequences of those rules. We know that 5 to the 0 is equal to 1 because of the additive law of exponents, right? You know that 5 to the 0 times 5 squared is equal to 5 to the 0 plus 2, but that's just saying 5 to the 0 times 5 squared is equal to 5 squared. Well, if 5 to the 0 times 5 squared is still equal to 5 squared, you better have that 5 to the 0 is equal to 1. There's no other choice. In a similar way, 0 factorial has to be equal to 1 so that the formulas we all agreed upon work out the way they're supposed to work out. Alternatively, you could argue to yourself, well, if n factorial is the number of ways of permuting n things, you could kind of say, well, how many ways are there of permuting or arranging 0 things? Well, there's one way, right? Because there's 0 things, there's one way of arranging them. There they are on the floor. They're arranged. There's the one way of doing it. There's none of them there. But there's still one way of ordering those 0 things. It's not a great argument, but it's not the worst thing I've ever said. Okay. Oh, watch out there. Oh, there's something. Oh, that's not that. Something else. Okay, cool. Right. Let's look at a couple more examples. Let's not get water everywhere. How much time? Oh, we got plenty of time. So another example here. A security code is formed by any arrangement of 4 different or distinct letters followed by 3 distinct digits. How many different codes are possible? And even though you could use the formulas I just talked about, I almost never use those formulas. Like, they just don't find them convenient at all. So let me show you, let's talk about 2 different ways you could do this. So just as a point of some examples, your code could be something like A, B, X, Z, and then 1, 2, 5. Or you could use the same letters and numbers and say B, X, A, Z, 5, 2, 1. And those would be 2 different codes. So you could do this using the formulas. You could say, well, from the 26 letters in the alphabet, I want to permute 4 of them. So I'm going to say, great, or I want to find the number of ways I can permute 4 of them. So it's going to be, I should really see P of 26 comma 4. That's the number of ways of picking your 4 alphabetical letters that are distinct, times your 3 digits that are, how many digits are there to pick from? There's one more. Yeah, but 0 is a valid choice. So or, as long as they say it is, right? But if they just said 10, any of the 10 digits, or they said any of the digits, and they didn't say you couldn't pick 0, then we should include 0 as well. So there's going to be 10 digits to choose from, and we want 3 of them. So this is looking like 26 factorial over 26 minus 4 factorial times 10 factorial over 10 minus 3 factorial. Honestly, this is not the way I would think of the problem. Here's how I would actually think of it. I would think of, cool, I've got how many choices for my letters? Well, 26 choices for the first letter, and since they have to be distinct, 25 for the next one, 24 for the next one, 23 for the next one. And then for my 3 digits, I have 10 choices for the first one, and they have to be distinct as well. 9 for the second, 8 for the third. That's another equally valid way of expressing your answer. I will point out that this right here is exactly 26 factorial divided by 22 factorial. I'm multiplying all 26 of the first 26 numbers together, but I really only want the first four of those, so I'm going to divide out the other 22 of them. Similarly here, 10 times 9 times 8 is really just 10 factorial divided by 7 factorial. One way to maybe make this a little easier to see, maybe, I don't know, 10 factorial over 7 factorial. Another way of writing this, instead of writing it all out, is you say, oh, it's 10 times 9 times 8 times every number, including 7 and after it. So times 7 factorial over 7 factorial. Oh, look, those exactly divide to 1. And you're left with 10 times 9 times 8. Okay. And now, switching gears a little bit, but not super a lot, we're going to talk about combinations, the number of ways of picking a grouping where the order doesn't matter. And I had a different example I think I would like to look at first. So, combinations where order is not important. So let's go back to that. Do I like that example enough for this? Yeah. Yeah, that's fine. Okay. So let's go back to our jam example. So back to 10 entries for the jam. And now the question is going to be slightly different. Instead of the number of ways that we can pick first, second, and third, how many ways can we select the three best jams? Meaning we're not going to differentiate between who's first, who's second, and third. We're just going to say these three jams are the best, and the other seven were trash. No, I'm just kidding. The other seven were perfectly fine. So now we don't care if you've picked this one to be first, this one to be second, this one to be third, or mix them up. So here's how this is going to work. We're going to say, well, I want to know the number of ways I can pick any three things. So I'm going to take, in fact, let's just say we picked, yeah, it's kind of a big number, James. Yeah. So for example, I don't care if I picked jams A, B, and C in that order, or that order, or this order, or this order, or this order, or this order. All six of those orderings of those three things still give me the same top three jams. And that'll be true for any three jams I picked, right? Whether it was jams E, F, and D, or G, H, and I, or whatever that I labeled them. So we're going to take the number of ways we could have picked first, second, and third place, and we're going to divide by the number of ways we could have ordered those three people, those three jams. So the way we're going to get this, we're going to say it's going to be, how do I want to say this the right way? It's going to be the number of ways of getting the permutations, but then we're going to also divide that by the number of ways you could rearrange the three winners so that we don't really care who's first, who's second, who's third. This ends up boiling down to being 10 factorial over 10 minus 3 factorial times 3 factorial in the denominator. So still the 720 ways you could have picked first, second, and third place, but then dividing by 6 so that we don't actually care who's first, second, and third. And so I want to do this example because I thought it was going to fit in nicely, but it's not great because there's too many possibilities to write down. So we'll do another one here where we'll actually see the things. But here, looking at this, is going to be 10 factorial over 7 factorial is 10 times 9 times 8 divided by the 3 factorial here, which is 6. And then we could actually calculate this. We can cancel and cancel. So it's 10 times 12, which is 120. So for these 10 jams, there are 120 different possible ways of picking a top three. Seems like a lot, but there are. Let's look at an example that's a little bit more countable. like we can actually write them down. So I feel like this is not exactly getting at what I hope to kind of display here. So let's look at this next example, which is a little bit more, I don't know, less interesting. Fine. So let's look at 8 here. So first we're going to start with permutations instead of combinations. So we're going to do both. So how many permutations of 3 letters chosen from A, B, C, D, E? Well, the formula we can apply, although I am gonna write them all down. But the formula, well, I'm not gonna write all of them down, maybe. But the formula would say, well, it's going to be P of 5 comma 3, which is 5 factorial divided by 5 minus 3 factorial. That's going to be, so I don't really want to write 5 times 4 times 3 times 2 times 1 over 2 times 1. What I would rather have written is say, I know it's going to be 5 times 4, sorry, it's going to be 5 factorial over 2 factorial. And then essentially, when I do this, I know I'm just cutting off the last couple terms from the 5 factorial. So it's going to be 5 times 4 times 3. And I know that the 2 times 1 on top is getting divided out by the 2 times 1 on the bottom. And that's going to be what, 60? So I'm not really going to write all of them, but I'm going to write enough of them so you can see what's happening. So by now, we've probably rearranged 3 things enough times that you know there are 6 ways of doing it. So if I pick A, B, and C, I could have A, B, and C, or A, C, and B, or B, A, C, or B, C, A, or C, A, B, or C, B, A. And for any distinct choice of 3 letters, there are going to be 6 different ways of arranging them, whether it's A, B, and C, or A, B, and D, or A, B, and E, or A, C, and D, or A, C, and E. I feel like I'm missing something. No, I'm not. Or A, D, and E, or B, D, and C, or B, D, and E, or C, D, and E. 2, 4, 6, 8. I always miss one. Which one am I missing here? I have A, B, C, A, B, D, A, B, E, A, C, D, A, C, D, B, D, C, B, D, E. Why did I write C before D? I think that's the mistake I always make. So this is B, C, D, and then I missed B, C, E. There we go. I knew there was one. Okay. Each of these combinations of 3 letters have 6 ways you could arrange them. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 6, which is 60 ways of permuting the 3 letters out of these 5 letters, which is what we said there was. But now, based on the way I've written this list, you can kind of see how many different combinations there are. So instead of how many permutations now, let's ask the question, how many combinations, where order doesn't matter, of 3 letters chosen from A, B, C, D, E? Well, you can kind of see them already. They're the top ones here. A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, A, D, E. I don't need to say the rest of them. You can see them all. There's 10 of them. I want to write an exclamation point to be emphatic here, but I don't want to because an exclamation point has mathematical meaning now. So I won't be using exclamation points willy-nilly anymore. And the way you can calculate this is by saying, well, it's the number of permutations we had, all 60 of them, divided by the number of ways you can rearrange the number of things you picked. So divided by 3 factorial in this case, which ends up being the notation. So let's write this out. It's going to be 5 factorial over 5 minus 3 factorial times 3 factorial. Or as I would write this, C of 5 comma 3, or 5C3. The number of ways of choosing 3 things from 5 things where order doesn't matter. So the only difference between the choosing function and the permutation function is the choosing function you divide by an additional k factorial, where k is the number of things you're picking. And this function is super duper cool. It is, you have seen this thing already probably many times in your life, and you just didn't know it. I'll tell you about it in a minute because I can't help myself. But I'll point out that more generally here. So, and by the way, this was equal to 6, sorry, 10. Right, we already wrote 10 over here. I don't know. Sorry, got a little distracted. So, more broadly, the number of combinations, not permutations, combinations of k objects chosen from n objects is C of n comma k or nck, or my preferred and everyone who likes math's preferred notation, n choose k, which looks like an n over a k with tall parentheses around them. It's not a fraction though, right? Don't write a little fractiony thing there. Is equal to n factorial over n minus k factorial times k factorial. The way I always think about this formula is the numbers in the bottom before you take their factorials should add up to the number in the top, right? N minus k plus k should be n. And this is called the choose function, and it is super, super useful. Useful, yeah, useful. So, for example, you all took, well, yeah, all of you have taken Calc 1 at some point. So remember back when you maybe had to so just going back for a minute. Remember when you maybe had to use the limit definition, I know, right, of the derivative? You don't need to write this part down, but you might be interested in what's happening here. To use limit definition to calculate f prime of x for f of x equal to x to the fourth. And you're like, well, how is this related? Well, trust me, it is. So when you did this, you wrote something like the limit as h goes to 0 of f of x plus h minus f of x all over h. And then that was the limit as h goes to 0 of x plus h to the fourth power minus x to the fourth power all over h. And then you had to multiply out x plus h to the fourth. And instead of doing that, what you might have done if someone showed it to you is you might have used Pascal's triangle. You might have said, hey, someone showed me a thing one time where if you look at Pascal's triangle, these numbers, that's a 6, not a 4, these numbers tell you the coefficients in the binomial expansion. So this row here is telling me that x plus h to the fourth power is 1 times x to the fourth plus 4 times x to the third plus 6 times x squared. Oops, I missed the h's completely. X cubed times h, 6x squared times h squared plus 4x times h cubed plus 1h to the fourth. And those coefficients exactly show you how to write it out in a kind of fast way. But here's what's really happening. These coefficients, those coefficients are all coming from the choose function. That one there is really a 4 choose 0, the number of ways of picking 0 things from 4 things. Because what you're doing here when you multiply out x plus h times x plus h times x plus h times x plus h. Let's actually say it's 4 choose 4, sorry. If you want to get the x to the fourth, you want to say, okay, how many ways can I pick 4 x's? Well, there's one way. Pick that x, that x, that x, and that x. Here, for this 4, which is 4 choose 3, how many ways, when you multiply this out, can you pick 3 x's? Well, I can pick these 3 and that h, or these 3 and that h, or these 3 and that h, or these 3 and that h. Oh, there's 4 ways of doing it. It's not a coincidence. This is exactly coming from here. So literally, this entire Pascal's triangle, every number in Pascal's triangle is coming from this choose function, which I just think is neat. I might be biased. I might have had a poster of Pascal's triangle when I was in high school. My mom gave me. I don't know why she gave it to me. I mean, she knew I like math, but like she had no idea that it was neat. She was like, "Here's a math thing." I was like, "Oh, this is cool." Like, oh. So anyway, um, it's a neat function. It shows and it comes up all the time in all sorts of places. But the place you might be most familiar with it coming up is in this binomial expansion when you multiply things out like this. But literally, it is the number of ways saying, I want to know how many ways can I pick this many things from this many things. It's this function, which is kind of cool. So let's look at some examples, which are less exciting, but fine. So let's say we have the following. How many ways can I form a committee of three of the people sitting in this room? Three of us, of which there are seven of us. Well, the answer is seven, choose three. We don't care what order we're picked in, right? It doesn't matter if it's me, you, or you, and me, right? That's the same group of three people. Doesn't matter that you got picked first or I got picked first. So that would be seven, choose three, which is 7 factorial over 4 factorial times 3 factorial. I don't like writing the 7 minus 3 part. I know that 7 minus 3 is 4. I know that 4 and 3 should add up to 7. So you know if one of the bottom numbers is 3 factorial, then the other number should be the difference factorial, and we can subtract. It's probably, so I would say if the numbers are small enough, maybe like less than 10, it's probably, you're probably expected to simplify this further, is what I would say, what I would guess. So this is not too terrible to simplify. 7 factorial over 4 factorial, that's going to be 7 times 6 times 5. That's this part right here, right? Because I don't need the 4, the 3, the 2, or the 1, but then I still have the other 3 factorial on the bottom. But then 3 times 2 times 1 is equal to 6. So the 6 and 3 times 2 times 1 cancel, and I get 7 times 5, which is 35. So from just the 7 of us, there are 35 different ways we could pick a group of 3. Or alternatively, there are 35 ways we could pick a group of 4. Right? If there's 35 ways of picking 3 of us, there's 35 ways of leaving out the other 4 of us. So there's kind of a neat symmetry here. It is also true that 7 choose 4 would be 7 factorial over 3 factorial. Oh, it's the same thing. It's also 35. We like to make the questions harder, though. What if 2 people in class don't really like each other very much and cannot serve on the committee together? How do we deal with that? Well, let's label everybody. So let's say that persons A and B can't be on the committee together. And then the other 5 people, peoples 1, 2, 3, 4, and 5, they can be on the committee. They're fine to go. So we already know there's 35 ways of picking 3 people. So then the question becomes, of the 35 ways of picking any 3 people, how many of those have both A and B? Well, if the committee has A and B, there's only one slot left. And there's only 5 different ways we can fill that one slot with person 1, 2, 3, 4, or 5. So you can have A, B times, or and then any one of the 5 people in that slot. So there's 5 ways. Meaning the answer to this question is 35 minus 5, which is equal to 30. I counted the total number of things possible, and I subtracted the number of things I didn't want. A lot of these problems there are multiple ways of approaching the meaning. You can either do it kind of subtractively here, right? Count everything and then take away what we don't want, or you could build it up. Count all the things you do want, but be careful not to overcount. So let's actually look at how you could build this up as well. So we could have thought of this as, okay, how many ways can we have just A and not B? Well, I can have A, and then there's two slots left. How many people are there to choose from for those other two slots? If I don't want B, you can show me on your fingers. You only need one hand because there's how many people left? There's five, right? So there's five choices there, four choices there. Or what I would say really is we have five choose two, which is 5 factorial over 2 factorial times 3 factorial, which is 5 times 4 over 2 times 1, which is 20 over 2, which is 10. That seems different than that. Oh, here's why. The way I did it here isn't accounting for the fact that order doesn't matter. It's counting choosing person 1 here and choosing person 2 here as different than choosing person 2 here and person 1 here. So that's why we have to be kind of extra safe here, make sure we don't overcount. So there's 10 ways of having a committee of the people with just person A, and similarly, there's 5 choose 2 equal to 10 ways for having just B and not A. And then thirdly, we could have neither A and B, right? We could have just the other 5 people, so neither of A and B. And then we have 3 slots and 5 people to pick from, so it's going to be 5 choose 3, which is also equal to 10. So there's 10 plus 10 plus 10. Oh, there's 30 ways of doing it, which agrees with what we did before. I'm not saying you have to do both ways here. I'm saying you can think of this either way. And as long as we are careful, you have to be careful, you can get to the right answer in 2 different directions. How much time is it? Okay, yeah, we got that. So I will point out it's a pretty common tactic when you're calculating things to, instead of build up, to take the total amount of things and subtract the things you don't want. That is a very, very typical way of counting the number of things we want, or later on calculating the probability of something we want. So let's look at this last, yeah, let's say last example. So a jar contains some marbles, specifically 5 green marbles, 4 red marbles, and 3 black marbles. So we're going to ask some questions. You randomly, I mean, you're not looking, you randomly scoop up 3 marbles. How many different possible ways, different's not a great word to use here. How many possible ways are there to get all green? In fact, let me do a little bit of picture drawing before we get started here, because I want to make something clear. So we have colors. I have colors. Sure, I have colors. Maybe. So we've got 5 green marbles in here. And we have some red ones, 4 to be precise. And we have three black ones. Where's my black pen? Sure. So it might sound silly because you might think, well, all green, there's only one way, they're all green. But what I would encourage you to think about here is that maybe all five marbles look a little different. Like maybe one's swirly, one's got dots on it, one's got stripes. Like they all look different, but we just care. I don't care which three green ones you pick. I just want to know how many ways I can pick any of the green ones and get three of them being green. Well, how many green ones are there? Five. I want to choose three of them. I would encourage you to use the word choose because I think it kind of, at least for me, it makes me, I don't know, it just causes me to be like, oh, I'm choosing three. I'm going to use the choose function. So it's going to be 5 choose 3, which we've seen enough times now to know that's going to be 10. That's 5 factorial over 5 minus 3 factorial times 3 factorial, which is 10. So there's 10 different ways I could pick three of the green marbles. Just like there were 10 different ways I could pick three of the first five letters of the alphabet. Right? In fact, you could think about labeling the marbles, the green marbles, as A, B, C, D, and E. And there's 10 different ways I can pick three of those green marbles. I don't care what order I pick them in. I just care that they're all green. Question? Exactly. Perfect. Yes. What if I asked for how many ways we could pick all three being black? Well, there's only three black marbles. So there's only one way of picking all three of them to be black. We picked all three of the black ones. That was the only way you got three black ones. And the formula does bear this out. If you ask how many ways can I choose three things from three things, it's going to be 3 factorial over 3 minus 3 factorial times 3 factorial. That's going to be 6 over 1 times 6, which is going to be 1. But also it makes sense, right? If you say there's only three things to pick, I'm asking how many ways can you pick those three things? There's only one way. You picked those three. There's no other way of getting three black marbles. It's kind of like saying how many ways can you pick the 5 fingers on your hand? There's one. You picked all 5 of them. Different than how many ways can you pick 4 fingers on your hand, right? You can pick these 4, or these 4, or these 4, or these 4, or these 4. There's 5 ways of doing that. What else have we got here? Sure. How about one of each color? This is where it gets more interesting. Well, how many ways can we pick a red one? Or a green one? Let's start with the green one. How many green ones are there to pick from? 5. How many red ones? 4. How many black ones? 3. Now, really, I should be using the formula here. What it should be saying really is, if I want to pick one of the green ones, there are 5 choose 1 ways of doing that. If I want to pick one of the red ones, there are 4 choose 1 ways of doing that. If I want to pick one of the black ones, there are 3 choose 1 ways of doing that. It is probably worth knowing that anything choose 1 is just that anything. 5 choose 1, you're asking, how many ways can I pick one thing out of 5 things? 1, 2, 3, 4, 5, right? I can pick my first finger or my second finger or my third finger or my fourth finger or my fifth finger. But there's 5 ways of picking one thing from 5 things. So, and I think this is worth knowing more generally, whenever you have n choose 1, it is always equal to n. So here it says 5 times 4 times 3, which is 60. Also worth knowing, in fact, I'm going to write 3 things down here. N choose n minus 1 is also equal to n. So if I said, what's the number of ways of picking one finger from my 5 fingers, there's 5 ways. If I said, what's the number of ways of picking 4 fingers, it's the same as asking the question, how many ways are there of excluding one of my fingers? Which is still going to be 5. I can exclude this one, or this one, or this one, or this one, or this one. So these are the same. N choose 1 is equal to n, and n choose n minus 1 is also equal to n. And if you look at the formula, it will bear this out. And then I feel like while we're on the topic, n choose 0, the number of ways of picking 0 things from n things is 1. How many ways can I pick zero of my fingers? One way. I picked zero of them. How many ways can I pick all my fingers? There's one way. I picked all of them. So n choose 0 is 1, and n choose n is also 1. Okay, continuing with this jar problem here. How many ways are there of picking 2 green marbles and 1 red marble? Well, at this point, hopefully the idea is kind of sinking in here. We're just going to see, well, there's 5 green ones. I want 2 of them, so it's going to be 5 choose 2. There's 4 red ones. I want 1 of them, so it's going to be 4 choose 1. And that's going to be 5 factorial over 3 factorial times 2 factorial times 4 factorial over, I'm doing too much work, 1 factorial times 3 factorial. This thing here, you should probably never write this out because we know that 4 choose 1 is going to be 4. I don't want you to spend your time writing this out, right? You get 4 times 3 times 2 times 1 divided by 3 times 2 times 1. Everything cancels except for the 4. So here we're going to get, that we know is 10. We're going to get 10 times 4, which is 40. Right, this is 10, right? Because the 5 factorial over 3 factorial is just 5 times 4, and 5 times 4 is 20 divided by 2. 2 factorial is equal to 2 is just 10. What have I said? I want no green. Well, again, this is an example of one of those questions you could answer in a number of ways. You could answer it by thinking of all the things you could get. You say, well, I could either get 3 red, or 3 black, or 2 red and 1 black, or 2 black and 1 red. I don't want to count up those 4 different things. Instead, what I really want to do is I want to calculate the total number of ways to pick 3 marbles minus, is this what? I'm like, minus, I want no green. Is this the way? I'm thinking of this the wrong way. Sorry. Sometimes it's hard. Sometimes you get jacked up when you think about this. I should be thinking of this more smartly here. How many not green marbles are there? I know you can't see the page anymore. There were 12 marbles total. 5 of them were green. So the other 4 red and 3 black means there's 7 marbles that aren't green. So from those 7 that aren't green, I want to choose 3 of them. Sorry, I think I was starting to think about the next problem already. And that 7 choose 3. Honestly, we should just leave it like that. Yes, we could leave it like that. I promise we can. Here's what I was actually getting at. What if I want at least 1 green? The number or words like at least or at most are kind of annoying because it usually means you have to do more. So I want at least 1 green marble. Well, I could either have exactly 1 green, or exactly 2 greens, or exactly 3 greens. So let's talk about how many ways you can get 1 green marble. Well, 1 green marble, there's 5 green marbles to choose from. I want 1 of them. What about the other 2 marbles? I want them to not be green. How many not green marbles are there? 7. Out of those 7 not green ones, how many do I want to pick? Or choose is the better word here. Well, I want 3 marbles total. I already picked 1 of them to be green, so 2 of them should be not green. Same idea for 2 green marbles. I want, of the 5 green, to choose 2 of them. Of the other 7 not greens, to choose 1 of them. And you can even apply the same idea for 3 green marbles. Of the 5 green marbles, I want to choose 3 of them. Of the 7 not green marbles, I want to choose 0 of them. You don't really need to write that part though, because 7 choose 0 is just 1. So this ends up being 5 choose 1, which we know is 5, times 7 choose 2, which is 7 factorial over 2 factorial times 5 factorial. 5 choose 2, we've done so many times, it's 10. 7 choose 1 is 7. 5 choose 3 is also 10. 7 choose 0 is 1. So you're getting 5 times, let's see, this thing right here, the 7 over 5 factorial is just 7 times 6. That's 42 divided by 2 is 21. Plus 70 plus 10, we get 105 plus 80, which is 185. Feels like a lot of work. There's a better way. So instead of counting up all the things we want, here is where we're going to count all the things that could happen by picking any three marbles and then subtract off the ones we don't want. So, or we could say, take the total number of ways of picking three to pick, or choose is the word I should say, any three marbles. Okay, how many total marbles are there to choose from? How many do I want? Minus what I don't want. So here, if I want at least one green, I want either one green or two green or three green. The only thing I don't want to happen is to have no greens. So I'm going to subtract off the probability or the number of ways to get no green marbles, which is 7 choose 3, which we already calculated. I guess I should have calculated it. Oh well, I didn't. So let's calculate these things and see what we get. It should be 185. But let's see. So we get 12 choose 3, which is 12 factorial over 9 factorial times 3 factorial, minus 7 choose 3, which is 7 factorial over 4 factorial times 3 factorial. And this is going to simplify to, so let's see. Here's how I'm thinking of this. The 12 over 9 factorial, sorry, the 12 factorial over 9 factorial is 12 times 11 times 10. Because then everything starting at 9 after is going to cancel out. So that's 12 times 11 times 10 divided by the 3 factorial still there, 3 times 2 times 1. The way I kind of think about this is when I'm canceling out the parts I don't need, the number of things multiplied together in the top and the number of things multiplied together in the top, if you write it out, should be the same. I have 3 things on the top, 3 things on the bottom. The same should be true over here. 7 factorial over 4 factorial, you want to divide by the bigger factorial thing, is going to be 7 times 6 times 5 over 3 factorial, which is 3 times 2 times 1. This always will be an integer because you're counting the number of ways of doing something. You can't do something half a way. So let's see. 3 times 2 times 1 is 6. 12 over 6 is 2. So we get 2 times 11 times 10 minus the 6 and 3, 2, 1 cancel, 7 times 5. So we get 220 minus 35, which is exactly 185. And I would say most people would probably argue that the second way of doing it is the more efficient or better way. It requires less kind of calculation. Yeah. 7 choose 3. When you say 5-0, what do you mean? Well, but the thing, so I'm not trying to say, so you're totally right. I should have said, so what I should have said here is I have all 12 marbles, choose any 3 I want, and over here I have all 7 not green ones, choosing 3 that I want, times choosing 0 of the 5 green marbles. Up here, no green, same thing. Well, because what I'm really thinking of is there's 12 marbles total, right? There are 3 black, 4 red, 5 green, or 7 no green, 5 green. So I want to pick all 3 to be not green, and well, oh, there's 7 marbles I can pick from. And then I could have said 12 minus 5 if you wanted to, but there's 7 marbles to pick from. I want 3 of them. Also, I could say I'm also going to pick 0 of the 5 green ones. So I'm going to multiply by 5, choose 0. But this 5, choose 0 is just equal to 1. So it doesn't affect our calculation at all. Same deal here. Yeah, we can't say 5, choose 0 because it's not enough, right? If I say 5, choose 0, I'm saying, well, I want to pick 0 green ones, but then I still also want to make sure I pick 3 marbles. Since I didn't pick any green ones, I have to pick 3 red or black ones. And let's call it there. A good stopping place. We'll continue talking about this stuff next Tuesday when we meet. Obviously, no class next Thursday because it's Thanksgiving, or Friday, not that we meet. And then, so we meet 3 more times. I know, it's not a lot, right? Tuesday and then Tuesday and Thursday. We'll talk about probability probably next time. which is really just dividing things by other things, and then we'll hopefully work up the base formula by the end of our meetings, because that's usually what kind of appears on your final exam. And base formula is really just a way of saying, if I know that the probability of testing positive for a disease, given the have the disease is something, how to reverse engineer it so that you know what's the probability that you have a disease given that you tested positive, which is much more important. That's what we're working towards. Have a lovely day. No, I'll see you on Tuesday. Have a lovely Thanksgiving anyway, but I'll say it again on Tuesday. Yeah, 10th is cool. Stop this. Yes.
We want to add me to the camera.
Oh yeah, yeah. Sorry.